Hi everyone, I'm excited to be here to talking about enhancing human-computer interaction through spatial computing. I will focus on how I use spatial computing to extend our abilities and seamlessly interact with our physical and virtual scene. Before diving into my work and the future, let's take a step back in time to a pivotal moment in our history. 2.5 million years ago, our ancestors invented the first tool, a simple but sharp stone, which we now recognize as the earliest form of knife. This simple but revolutionary event marked the beginning of the humanity journey to extend our ability and change the world. From that moment, each tool we invented, whether it was a knife for cutting or a wheel for moving, they all represent a new way of interaction. As our tools evolved, so did our interactions. HCI, in a high level, it is about how we use a digital tool. HCI began to take shape in the 1940s with von Neumann architecture. Back then, interacting with computers needed binary sequence on punch card. But even then, HCI was about extending our abilities to interact with data. The 70s brought the command line interface. It made interactions simpler, but still not for everyone. The real breakthrough was the graphical user interface, came in the 80s. It made computation and the interaction way more accessible and intuitive for everyone. Starting from 2000, smartphone became ubiquitous and increasingly integrated into our everyday life. Now with spatial computing, such as VR, AR, MR, XR, we are paving the way for the future metaverse. So what are these R's? Confusing R's exactly. Our first impression might be separate display for each eye so that it can create a stereo display. But more specifically, VR stands for virtual reality. Everything is in VR is computer generated with no visibility of the physical surrounding. AR stands for augmented reality. We can look through transparent optics to see the real world directly, while digital content is overlaid onto that view. MR stands for mixed reality, which is somewhere in between. Some MR just use video pass-through, and some other use superimposed digital contents in your physical view. In general, it focuses on the interactivities between the physical and the virtual world. So at the end, we use an umbrella term, XR, to cover them all. XR is basically input and output interface for the future metaverse, like keyboards, mouse, screens, and even smartphones to us. What we are experiencing today, VR is just like it's the transitional state. Spatial computing represents a broader concept of XR, serves as a branch of HCI. It is oriented towards how we will engage with the metaverse in the future. So currently, XR mostly focuses on stereo display and spatial audio, but they are only a fraction of what spatial computing has to offer. In the future, we can expect it to simulate multisensory cues and engage our entire perception of reality, not just the sight or sound. It will be about smell, touch, taste, movement, and body awareness, and even body movement. Let's look at some example about the multi-sensory simulation. In Ready Player One, human players represented as avatars can get fully immersed in car races and social activities using treadmills for movement and haptic suits for full body feedback. These technologies are available now, but the next level of simulation is shown in the Matrix movie. Characters live in a fully simulated reality that is so convincing so that they cannot distinguish it from the physical world. Their senses and movements are digitally simulated, but they believe it to be real. Future spatial computing should help us interact with the virtual world as easily and as naturally as with the physical world. But even we have so many great digital tools like Adobe or Autodesk or all sorts of that, many of us still prefer to get a pen and paper to sketch, to brainstorm or illustrate ideas. This shows that they are still not very intuitive or natural. Ideally, learning and using spatial computing interfaces should be effortless. They should adapt to us instead of the other way around. Sci-fi movies like this offer possible solutions where gestural and spatial interfaces seem easy to work with the digital content, but practically, I'm not a fan of the gesture interface in Minority Report, but they definitely look cool and represents some advantages in some kind of scenario. The next level of natural user interface or intelligent assistant. Imagine something like Jarvis from Iron Man or Edith from Spider-Man for everything in our life. They won't just respond to gestures or voice commands. They will anticipate our needs, provide context-aware support, and interact with us in a way that feels intuitive and human. So the nature of spatial computing and even HCI in general, so it's extending human abilities. Just like print extends communication or wheels extend our mobility. The early concept was explored by Marshall McLuhan in his book published in 1984. Building on this idea, I developed my own theory for spatial computing in two key areas, intrinsic and extrinsic extensions. Intrinsic focus on our inherent abilities, such as perception, cognition, movement, and decision-making. Extrinsic aim to enhance how we engage with the physical and the digital surroundings. These two areas are the two legs of my research. More specifically, innovating multisensory simulation for perception, investigation, assessment, and rehabilitation. And then it's designing novel intelligent assistants that leverage AI, robotics, and multi-modal inputs to provide context-aware support. So now I'll dive into the first area. Our goal was to study sensory integration, cognitive load, and perceptual abilities for human balance. So we need controlled and repeatable conditions for the assessment and intervention. That is why virtual environment stands out as experimental testbed. I designed 5 virtual environments for different purposes. The first 4 scenes simulate what patients experience in their daily life. The start scene is an abstract scene for challenging the patient's vestibular system and proprioception, which is a sense of body position. For now, we use this like bare bone and simple graphics because perceptual and sensory disorders are mainly triggered by visual flow, not by realism. If graphics are high fidelity but not good enough, they can cause distractions for the patients and even the uncanny valley effect. So we kept it simple as a compromise. The scene also has the auditory stimuli. In the scenes, the content and the intensity of stimuli are highly controllable. So we can effectively evaluate how participants respond to challenges in balance assessment by applying the stimuli in different levels of intensities. On the other hand, the intervention sessions gradually expose participants to overwhelming stimuli so that they could build a resistance and adaptability over time. So let's feel the high and low intensity. Oh, for some reason the audio is not clear. So that's low for airport. That's high for the airport. Now it's low for subway. And these are one of the reasons that some people don't like to live in New York because it's so bustling and a lot of people. Yeah, but anyway, I integrated spatial audio in the scenes. With spatial audio, the environment can provide a better sense of presence and overall user experience, which is important for both the clinical and the research setting. Sorry. In balance assessment, we use standardized and repeatable tasks under various experimental conditions. So we can study intrinsic balance capabilities by collecting data, establishing a baseline for balance, and identify the problems, and evaluating fall risks. There are three major emerging technologies in my system. Eye tracking. It provides saccade fixation and pupil size. They can help us study attention and cognitive load by investigating how we process visual information. Motion capture allows us to track precise body motions and analyze motor patterns. Pressure sensor can also get us some motion from the weight distribution and stability. Unlike the mocap system, which relies on the visible motions, pressure sensor can detect subtle changes in the underfoot pressure. For example, in standing balance assessment, we want to study how much effort needed to maintain balance. As we see in the pressure heat map, the participant is slightly leaning backwards, and their stabilization is working all the time. The micro adjustment and the stabilization effort are fully captured by the underfoot pressure. But the mocap system won't be able to do it because there is no visible motion. So to capture that micro stabilization, we can use a frame-by-frame difference as a very simple solution to get all the effort that the participant did in the study. From the heat map, we use the computer vision method to get additional balance parameters, such as foot dimensions, orientation, width of stance, width of support, or central pressure. With the data from this technology, we use existing or our own algorithms to measure and diagnose the participant. And then we use the measurement and the diagnosis to guide the further intervention for better outcome. For the intervention, our target group was people who are at the risk of falling, particularly the patients who are vulnerable to sensory overload, such as older adults, Parkinson's disease, individuals with vestibular disorders, or those recovering from strokes. Sensory degeneration in these groups can lead to anxiety and increase the fall risk when exposed to overwhelming stimuli. My research on balance for the aging population has a significant impact because falls are the leading cause of injury for people over 65 in the US, according to CDC. Traditional rehabilitation often requires physical settings that are difficult to set up. In contrast, our VR-based intervention system provides an immersive and personalized rehab that has highly controllable content and conditions. Therapists can easily control the scenes, intensity of stimuli, such as how many cars and how many planes and how many people walking towards you, all of that, and the repetitions of the trials in a few clicks. The existing part is that my system are not just used in our lab. It's being used in other research and clinical settings as listed. From the feedback we have so far, participants are showing improvements in balance, gaits, and conditions in navigating complex virtual environments, and the improvement transferred to their daily life. This research track contributes to improve human performance and well-being, and could help contribute to the future healthcare. Most of the work was done during my PhD, where my dissertation was virtual reality for human balance assessment. These projects were funded by NIH, NSF, and NYU. So we have seen how my work can extend our intrinsic capabilities. Let's move on to the second area. How spatial computing can create new forms of interaction that makes more intuitive, creative, and intelligent. For many of us, including myself, creating assets in 3D is not easy. It requires skills in 3D modeling, animation, and programming, which most people don't have. Even for simple sketching, many people still prefer a pencil and paper for faster prototyping because digital tools are often too complicated. So what we can do about it? I have explored how to use AI to use spatial computing more intuitive for everyone. But using data-driven content generation and multimodal inputs, so that we can empower everyone, not just the experts, to create a high quality spatial content. So let's dive into one of the projects. So the goal was to improve 3D model retrieval for non-professionals. So imagine that you are dealing with a large 3D set library. Finding a model with certain features can be very difficult. If you don't know the exact keywords, name, or only have a vague idea of what you want, for example, retrieve a 3D table with a swirly lag. Swirly lag is time-consuming if you don't know the artistic style. Or it can be hard for users to get the right airplane if you don't know the manufacturer or the model. We tackle this problem by using multimodal input cues, including text, sketches, and images. Instead of using the keywords or the name of the artistic style. So you can simply describe the table as in text, or provide a rough sketch like how I did with like a spiral feature, and upload a reference image. The system will combine all you provided, help you make the lookup and find the matched candidates for you. So our approach begins by creating a data set, which contains each 3D model from the 3D asset library and the encoding of its corresponding renderings from 3 different viewpoints, front, back, and perspective. These 3 images are encoded using clip, which aligns image and the text embeddings into a shared feature space. And the embeddings are stored with its corresponding 3D mesh. This step is basically, so you can imagine, you can think it that we are constructing the database for retrieval. And what we inputted is a combined query for that database. So the novelty of our work was how we handle the multi-model input. The system can retrieve the results based on more than one input. It fuses the latent embeddings of all inputs according to the user provided weights. This fusion is like a comprehensive search query. The weight can control how much influence each input has on the final query. So after computing the cosine similarities between the fused latent code and the constructed data set, the system will provide top K candidates who have the higher similarity. So just want to elaborate on the weighted fusion. So we take the weights of each input and multiply the latent code by this weights to fine-tune the output results. Here we see a sketch of a table is given as 0.1, and a sketch of its swirly lag as in spiral feature at 0.9. Then the system knows I focus more on the spiral feature and give me this blue chair, which is not correct. That sort of look like what I draw, but you know we want that. To fine tune, we add the text, a table, or a desk, or a sofa, or no matter what you want, or even a bed to get what you wanted. So the system will fine tune the result for you based on the updates of the weighted fusion. So in general, it is like having intelligent assistant that can understand and blend multi-model inputs to help you find what you're looking for without needing any technical skill. Another content generation project I worked on was for screen generation and authoring with the media hand sketching and the generative model. It focused on rapid phototyping and also designed for people who don't have any professional skill set. Integrating natural input modalities for terrain generation is challenging. Our solution was to use hand tracking and a generative model to simplify the process. With positional hand tracking and hand gesture detection, we can use our bare hand to draw in the mid-air to indicate desired shapes for the landscape, such as mountains, mesa, canyons, and volcanoes. So, like what we can see from the video, that you can draw like easily as you are like playing with a clay or whatever, but the input is a stroke. The more important part is that you can use it with your bare hand. You don't need any additional equipment. And also for the triggering, it's also gesture detection. So with that, you don't need any additional equipment to do whatever you want. So the generative terrain synthesizers then generate a realistic landscape, which combine features of our training data and the media stroke. We also provide authoring tools to modify the terrain, such as deleting, adding, repositioning, shaping, and changing steepness. So the pipeline of the system starts with a gesture interface. As you sketch in the air, the system reconstructs a placeholder terrain in a way that it's a ridge aligned with your drawing, and the base of the terrain expands to the ground level, so it gets the classic mountain shape based on what you drew and the spanning to the ground. So it's a typical mountain shape. So this step establishes the general structure of the terrain. It then converts this placeholder terrain into a raw height map. For the next, a CGAN-based image synthesizer is used to add realistic natural features to the height map. Finally, the processed height map guides the reconstruction function to generate the final terrain with realistic landscapes that mimics natural characteristics while preserving the overall shape that we provided through the media stroke. Our experiment made a comparison and shows that by adding a noise function, in our case, we use a poly noise because it can somehow mimic the natural variations. And we put it here between the raw height map and the GAN model so that it can increase the final natural variation, so that it can create better variations of the natural characteristic. So we have covered how AI with multi-modalities can help me with content generation. Now let's take this concept a step further and explore how robotics assistant can extend human capabilities and transform how we interact with the physical world. So I always dream to command a group of robots to rearrange objects on my desk, or even set a table for dinner, just by telling them where to move things. With our multi-robot system, this becomes reality. Instead of controlling each robot individually, you can give object-level instructions like move this cup here or push that book there, and the robots take care of the rest. So the key innovation here is a concept of object-level interaction. It is a natural way for us to communicate and interact with the robot. For example, in a cooking and dining experience, it can help me to fetch the proper utensils, set up the table, bring food, and clean up the table without having to tell them that move objects like in which digit or number from position X to position Y. You just naturally tell it to do it. So intelligent assistant like this can autonomously handle routine or repetitive tasks, allowing us to focus on more important activities or creativity. So imagine that you are setting a table for 20 or even more, then you can use this interaction to command multiple group of robots to do the same thing as you did for setting the table. So with the system, we explore some interesting interaction. For example, the robots can provide haptic feedback. They can push physical proxies and align them with their virtual twins so that it creates a haptic feedback to simulate the resistance caused by pushing objects. By adding more robots to my left hand, according to the video shows, but it not necessarily need to push to my left hand. So I feel like I'm pushing a heavier object. So the haptic feedback makes the experience more immersive. So we designed a multimodal interface for the system. The interface includes tangible manipulation. We can physically manipulate the object to show the robots exactly what we want them to do, and they just copy they just copy what we wanted and to push the target object to the target direction and the position. The graphical user interface features a live stream of the workspace captured by a top-down camera. Users can drag and rotate objects on the GUI to specify their target positions or even draw a path for them to follow. The speech input allows us to naturally refer to object by name. For example, commands like bring me the cup enable verbal instructions, making the system hands-free and intuitive to operate. The object has to be recognized by computer vision, and the names has to be registered to the objects before we can call them by name. Gestural interaction allows users to manipulate out-of-reach objects. So there is a ray casted from the user's hand for targeting, and the pinch as a gesture for confirming the object selection. In general, this system controls its rule-based. So this system so far is rule-based, but it has a lot of limitations and constraints. But like it's a strong demonstration of how intelligent assistance and spatial computing can be extended. So it can be demonstrate how intelligent assistant and spatial computing can be extrinsic extensions of ourselves. I can imagine how the AI-driven robot system in the future will deepen this transformation even more. Here's another robotic project I worked on. It is a shape-changing robotic interface that we designed and built from scratch. It demonstrates how robotic systems can extend our capabilities by dynamically adapting the shape to suit different tasks and environments. For example, the grid can transfer itself into a chair, a bed, or even a dynamic tabletop display. It's built from modularized self-lifting unit that can move up and down independently and collaboratively create a versatile and scalable surface. The project is focused on the robotic design so far, and we are working on the multi-model user interaction for it. But the preliminary results support that intelligent assistants as our extrinsic extensions can change our surroundings in response to our needs. As I look into the future, my work aims to push the boundary of the spatial computing across multiple areas, from enhancing perceptions and creating more intuitive, natural user interfaces to advancing intelligent assistants and designing solutions for people with different abilities. In the meantime, so I'll talk about other opportunities and concerns that when we develop this innovation. So in general, my goal is to make the spatial computing more immersive, more natural, more intelligent, more accessible, more secure, and finally, more impactful. So for perceptions, my longer term goal is to model each perception mathematically, so that we can simulate entire perceptual experience in virtual environment. But for immediate step, I want to try some early prototype that simulates smell and taste using chemical cartridges or diffuser. And by using auditory cues, we can have an illusion of feeling. Like spatial audio can do a lot of things. By using it, we can have an illusion of having a sense of touch, weight, and the texture without any physical involvement. So this is a part of pseudo-haptics, which is an area that psychology has been researching for a long time, but it's still relatively new to computer science. Our lab has completed a comprehensive literature review on this topic, and I'm part of it. We submitted to our survey paper to CHI 2025 a few weeks ago. So the future of natural user interface will be more than gestures and the voice command. Researchers started to explore brain interface-based interactions using technologies like EEG to read brain signals and translate the signals into command. This could be a game changer on how we interact with the world, making it a true extension of our mind. But there are immediate opportunities to enhance our interaction, such as using inside-out tracking for full body motion. Currently, tracking systems are often limited to a specific area because we need an external sensor. But with the full body inside-out tracking, we will be able to naturally walk, jump, dance, or even do sports in virtual world. This level of interaction would revolutionize applications for games as well as training simulations for remote collaboration and healthcare. Another immediate opportunity is drawing in 3D. When we reach out to draw in space, our arm naturally moves in arc rather than a straight line. So the drawing is not as precise as we do on 2D plane. To address this, we'll need to develop interfaces that account for natural movement patterns, possibly using AI to predict and compensate the movement in real time. So for another level of natural user interface, our idea is a lot of researchers have been doing a lot of work to improve this field. But my idea would be, my goal is to accelerate the advent of Jarvis. So I can imagine the intelligent assistant like Jarvis not just helping you individually, but coordinating across teams. It will be able to control a group of robots and assist us in a group meeting or teamwork. It can do tasks like taking notes, suggesting relevant information in real time, task and timeline management, and hands-on assistance. One good example is that online conference platforms like Zoom have live translation and caption, and some has intelligent meeting companions to take notes and summarize the meeting. So beyond the digital paradigm, I'm also looking at versatile, intelligent, and safe robots and drones that can help us with physical tasks like cooking, assembling furniture, or even search and rescue mission. The ultimate goal is to make them natural, responsive, and unobtrusive. So it is like they are always there when you need them. Otherwise, they won't be noticed. They won't be noticed if you don't need them. One of my immediate next steps is a collaboration with NYU Agile Robotics and Perception Lab. The project is to explore how multiple users can collaboratively control civilian drones for rescue and navigation missions. Intelligent Assistant will also help us maximize our ability to build and alter virtual world. I plan to use a novel view synthesized methods like NERF and Gaussian splatting to reduce the effort of creating realistic digital assets for virtual space. Beyond that, I want to push style transfer beyond a texture level, but at a contextual level. Imagine the physical settings of your home can be transformed into a cave. Your chairs could become stones, and your fireplace could turn into a campfire. Everything can be mapped from your home structure to fit the target theme. As we can see in this style transfer animation, it's mostly texture level style transfer. This is just a representation of what the future looks like, but the future would be a higher level than this. For example, the couch won't be couch. It won't be like, if let's say if it is a cave, then the couch would be like the stones with the shape like a couch. So spatial computing has large potential to alter and change perceptions, so nobody has to lose certain feedback regardless of their different ability. For example, a person with low or no vision could navigate complex environment through enhanced auditory or haptic cues. Intelligent assistant and brain computer interface can be game changer in this way. They can provide personalized support depending on individual need and further increase the independence for those who typically require special care. For example, a person with limited mobility could control their home environment, access information, or even perform tasks like cooking through multimodal inputs, such as voice command, eye tracking, or brainwave signals, as we can see from the video. In the future, spatial computing will become everywhere, just like what smartphones to us today. It will generate large amounts of data from users' locations and movement to gestures, interactions, and even biometric information. The spatial computing device won't be as clunky as we can see today. They will deliver services to billions, relying on the high-performance computing on the cloud over high-speed or low-latency networks. The large amount of personal data opens up opportunities for data science. It also brings the critical concerns about privacy and security, and so that protecting our sensitive data from breaches and misuse will be very important. But I'm not an expert in any of this area, but I believe I could raise them so that we won't miss it because they are so important. So as we continue to advance in spatial computing, I hope I can contribute my expertise to a future where spatial computing is both innovative and responsive and responsible. At the end, spatial computing is one of the next great tools in our long history of extending human capabilities. Just like the first stone knife, it has the potential to fundamentally reshape our understanding about ourselves and how we interact with the world. So let's look forward to it. Thank you. Okay, I'm ready to take questions. Yeah. Validate the result? Yeah. So more specifically for the human balance and the rehabilitation system, we did a instrument validation because back in 2019, so the dominant VR headset was HTC Vive and Oculus Rift, but they were not validated for the level of precision of our work, and it's not validated for the motion test that's recognized by the whole world, which I mean medical or physical therapy research. So we did a validation system. We did a validation study for that to VR headset, but we didn't do validation for the mocap because the mocap we used was OptiTrack, which is a gold standard. Yeah, so we published a paper in 2019 about the work, and then we find out that these two headsets was not perfect when we do vertical displacement. Yeah, so, and we mentioned in this paper that for researchers, we should be cautious that when we want to do like vertical displacement. And it's not perfect, I remember, in pitch and yaw, it's not perfect. Otherwise, it's okay. Yeah, so that's what we validate the data for the instrument for assessment and rehabilitation tasks. Yeah, but for the others, like the train generation or for the other projects, because we didn't really assess anything, so we didn't validate the equipment. Sure. Mm-hmm. You're talking about the project that use object level instructions for moving stuff, right? Is that the one you're talking about? Oh, I see. I see. Yeah. So actually, that is a paper we are waiting for the results. I'm not sure I can share more information, but the idea is that we want to interact with our environment, and that paper is actually targeted for smart buildings. When talking about smart building, I meant that maybe like a few decades later, if we walk in a building, we don't need to take an elevator. And the floor or the ground will deform itself and elevate you to the second floor or whatever. And so this is a concept for us to show our vision about the future, which has like an interactable environment. And in that one, we demonstrate some like other examples, like the deformable like rooftop or deformable walls. It's all connected to the idea that our environment can be interactable with you. Yeah. Mm-hmm. Oh, yeah. Yeah, that one we use a fabrication on top of that shape-changing surface, and so that we use projections for people to for like the audiences to understand that what the VR user is experiencing. But actually, the projection is not important for the user who is wearing the headset, because they can feel the virtual environment inside of the VR world with the headset display. And we use that video to demonstrate to the reviewers that what is actually what they are trying in the VR scene. Yeah. I think for that side, it's tricky because sometimes if you want to convince the whole world that some of our work can be applied to application, that is hard, because it's the one party that if people use it, I mean, for physical therapy, they don't have problem with it, because all they want to do is to have stimuli. As long as they have stimuli, they don't really care if it is like if the scene is validated or not, or like or NIH found them or not, because according to a clinician that I work with, who is in Israel, they told me that they began to use the VR for interventions and for assessment for a few years, and some of the and he said that one of the important hurdles to use that in real application is actually sometimes it's not covered by insurance. Yeah, it's not exactly what I expected in the first place. So I mean, for that question, I think as a researcher, I think one part is that we need to provide the solid result to convince the whole world that this is the future, this is efficient, this works. And another side is, which I think is a pragmatic side. So in order to push it forward, then we need resources. And then if the people use it, people can put more money on it, and it has a future. Then we probably need to convince the insurance company that you need to cover this. And maybe we can send a package to a patient's home. Then the insurance company maybe will lower their fees, so that if they practice at home, they are less likely to fall. And we are trying to close the circle, but it's not there yet. But I can see that even maybe a decade later, or even more or less. So we will get there.
I have a your mind is
Mhm, right. this idea just recently came to my consideration for the past several months. According to my understanding about this field, I think I didn't see any like good solution for now. Yeah, because let me give you an example. So, our brain is a very complicated and interesting stuff because it's hard to imagine now, but if you ever try to stand like in front of a cliff, actually a crazy idea will jump out, which is, I want to jump. And then if there's a robot you are controlling and get your idea and push you off the cliff, that would be dangerous, right? So I think this is still an open research. So this is not well researched according to my preliminary research review. So I think we need to, that's the reason why I brought it up, that Iron Man is cool, but the reason why I also attached Edith's like video for that, because if you watch the Spider-Man, you probably still remember that he has a crazy idea that he wants to, like, he mentioned that, is that a target? Which is one of Spider-Man's classmates. And the AI got this wrong idea and shoot out a missile to his classmates. And then he has to destroy the missile himself. So that's one of the reasons I mentioned that this is a critical part, and we cannot let AI to take over the world, especially when our brain has that dangerous idea, when we like have special conditions. So I think this is an open question, open research question, and I will definitely like explore more about it. Any other questions?
I have like one maybe similar question with inside, and I mean not just like cases one call it.
Oh, yeah. And for that inside out tracking, according to my current knowledge, so inside out tracking is still not perfect because people have been using like external trackers attached to their feet because, you know, for the headset, it has multiple cameras surrounded. And so what it can do is to capture your hand, because hand is easier to do, because when you use your hand, you always lift it up or do something around you. But they are not perfect because if you put your hands behind your back, they are not tracked. But this is information. This information is not important for us as users, but it's important for us as observers, because in the future, if we want to have a free and natural conversation with others, we will probably see each other in avatars, or like the Kodak avatars that Meta has presented, like in the talk between Mark Zuckerberg and the MIT, a person from MIT. They had the Kodak remote meetings in XR as in avatars, but the avatars look very like themselves. And so in that way, they didn't show their like arms or the whole body. They just show their upper body. That's the reason. And so the state of art is that I've seen like people using egocentric cameras to capture their feet, but their feet is usually not precise. Their motion is not precise. And for the external trackers, they use inside-out tracking, combines the cameras and the SLAM on that tracker on the feet. But there's the one condition that I do think there's still having problem, which is when you stump your feet. When you stump your feet, then it will mess up the IMU data. Yeah, so that's the crazy part. So I don't think they want to like advertise it and to say that, wow, this is the perfect solution for insider tracking. And then I don't think researchers will use the insider tracking, especially for the feet, if they they're seriously considering scientific assessment on the data. Yeah.
Thank you very much.
Thank you. Thank you for inviting me to the talk.